This lecture is about let polymorphism. So previously, we discussed the two languages that support polymorphism. At one extreme, we have a system F, and at the other extreme, we have predicative polymorphic lambda calculus. And another name for system F is impredicative polymorphic lambda calculus. So in the case of system F, we have a single syntactic category for types. The types are this function type variable, and this polymorphic type. And we have only one syntactic category for types. In the case of a predicative polymorphic lambda calculus, we stratify the types into two layers, monotypes and polytypes. Monotypes do not have a polymorphic types, so it is either function type or type variable. Remember that type variables themselves are not polymorphic types. It is just unknown types that we do not know anything about. The polymorphic types are always start with this type quantifier, or it is monotype. So in this way, we have two kinds of types, monotypes and polytypes. And of course, the polytypes include monotypes. And at the level of expressions, and there's also a big difference. In the case of system F, expressions have these lambda abstractions. And because we have just one single syntactic category, this variable x in lambda abstraction can have any type. But in the case of a predicative polymorphic lambda calculus, expressions have this lambda abstraction where the type for variable is restricted to monotypes. So in other words, this lambda abstraction can take as an argument only expressions of monotypes, not polytypes. So that's the main restriction placed on predicative polymorphic lambda calculus. So we have different definitions for types and expressions. And as a result, in the case of system F, the language is very expressive. It's a huge and expressive power, expressive. But the downside is the type reconstruction is undecidable. So it is very powerful, but it's very powerful, but it's not quite practical because the type reconstruction is undecidable. On the other hand, the predicative polymorphic lambda calculus has precisely the opposite properties. It is much less expressive, but it regains the decidability of type reconstruction. So it is decidable, which is good, but it's less expressive. So this predicative polymorphic lambda calculus allows us to define polymorphic expressions. So for instance, we can have this polymorphic identity function, capital lambda alpha, lambda x alpha, variable x. This guy has a type for all alpha, alpha error alpha, and it is a valid expression in predicative polymorphic lambda calculus. So this language allows us to create polymorphic expressions. But because of the restriction placed on this lambda abstraction, where this variable can take only monomorphic type, we can never use these polymorphic expressions polymorphically, which defeats the entire purpose of introducing polymorphic types. So on the surface, this language supports polymorphism. But in reality, it's not useful at all. So it's much less expressive. Now, we'd like to locate some sweet spot between this predicative polymorphic lambda calculus and system F somewhere lying here. And ideally, this language should have the best of both worlds. We'd like it to have decidability. So the type reconstruction should be decidable, and it should be sufficiently expressive. It does not have to be as expressive as System F. System F is a really expressive language, and we don't need the expressive power of System F. We need at least the expressive power that enables us to use polymorphic expressions polymorphically. So, to summarize, we'd like to identify a language that lies between predicative polymorphic lambda calculus and System F so that its type reconstruction is decidable and it's reasonably expressive enough that we can define polymorphic expressions like this one and use it really polymorphically. Unlike predicative polymorphic lambda calculus, which does not allow use this polymorphic expression really polymorphically. So we'd like to find some sweet spot somewhere here. We can think of this language as a compromise between this one and this one, in the sense that it takes the best of both worlds, decidability and expressive power. And the answer to this quest is let polymorphism. So let polymorphism is, the best way to describe let polymorphism is an extension of predicative polymorphic lambda calculus with let binding. So in other words, let polymorphism is predicative polymorphic lambda calculus extended with this let binding. So this let binding has this syntax: let x u in this is actually colon expression e in expression e prime. So what this construct means is that we find this variable x of polymorphic type u to this expression e, and then inside expression e prime you may use this variable x many times. It's just like let binding in OCaml language. So we are going to extend this predicative polymorphic lambda calculus with the new language construct called let binding, and then we obtain this let polymorphism. Here is the prototypical example of using let binding in this language. So we have this let construct, and this f has this polymorphic type for alpha, alpha arrow alpha, and the definition is polymorphic identity function. So we created this polymorphic identity function. This is a polymorphic identity function, and is bounded to this variable f of a polymorphic type. And inside this let construct, we are going to apply this function f really polymorphically. First, to Boolean type. Now this guy has a type bool arrow bool. And second, we are going to apply to integer type, assuming that we have integer type. It has type integer arrow integer. And then we can apply, for example, this one to Boolean constant true, and this one to integer 0. So now we achieve what we really need in practical programming languages. First, here, we can declare a polymorphic function, an expression of a polymorphic type. This is a polymorphic identity function, which has this polymorphic type. So the language supports polymorphism, polymorphic types. And here, we witness that the function f is applied really polymorphically. We use the same function f here and here in two totally different contexts. The first that uses Boolean type, the second one that uses integer type. So we are applying the same function f in totally different contexts for Boolean type, for integer type. So to summarize, we define a polymorphic function and apply this polymorphic function really polymorphically. So that we achieve what we really want in practical programming languages. So that's basically the key idea in lab polymorphism, which is an extension of predicative polymorphic lambda calculus with this let binding. Let's formulate this let polymorphism. So similarly to predicative polymorphic lambda calculus, we have two layers of types. First, the monotypes. A is function type or type variable, and also polytypes. U is this type quantifier, polytype, or monotype. And what about expressions? So we inherit everything from predicative polymorphic lambda calculus. So we have this lambda abstraction, lambda application, and type abstraction, and type application. But now we have a new language construct, which is let binding, which is a let x colon new expression E if expression E prime. So now we have two sources of variables. The first, lambda abstraction. The second, let binding. Every variable from lambda abstraction has a monotype here. But in general, those variables from let binding can have polymorphic type. Now, unlike the predicative polymorphic lambda calculus, variables can have polytypes because of this variable. So typing context now is either empty or type finding, and this time it is not A. In the case of predicative polymorphic lambda calculus, this is the only source of variables, so it is monotype. But this time, we have a second source of variables, namely let binding, which can create the variables of a polymorphic type. So in general, this is going to be U now. And then we have type variable declaration. And the typing rules for the existing language constructs, these four language constructs, are identical to predicative polymorphic lambda calculus. And for this variable, we have a minor difference. How do we type check the variable? And the difference here is now this variable can have, in general, polytype. Here, polytype, not monotype. So this type binding must be found somewhere inside the typing context gamma, in which case we deduce type U. And we need a new typing rule for this let binding. So how do we decide the type of this let binding? So actually it is easy to define the typing rule for this let binding because there's no type reconstruction. The type for this expression E is explicitly specified in the let binding. So as indicated by this polytype U, which says that we expect this expression E to be of type U, otherwise it wouldn't type check. So first, we verify that expression E indeed has a type U, this polytype. And then we augment the typing context with this type binding and then check expression E prime. And it turns out that we can either assign a monotype here, or alternatively, it's fine actually to assign polymorphic type here. But for simplicity, let's just assign monotype. In reality, the two choices make no practical differences. So, but just for simplicity, let's use this monotype here. So this is the typing rule for left binding. So we have developed the syntax and typing rules. And the reduction rule for this left binding is also straightforward, just like the left binding in OCaml programming language. So how do we reduce this left binding? So this variable x is bound to this expression E. So in the style of call by name, we could reduce it to E for x in expression E prime. If we prefer this call by value style, we will require this expression to be reduced to value v first, and then substitute value v for x in expression E prime. So this is the reduction rule for left binding. So that's pretty much the essence of left binding. The new type system called left polymorphism. And it may appear like this left binding is a syntactic sugar because it looks like lambda abstraction composed with a lambda application. So what I mean by that is, let's compare this left binding, let x u e expression E prime, and this lambda abstraction, lambda x u expression E prime applied to expression E. According to the reduction rule for left binding, this one reduced to E for x in expression E prime. And if we apply beta reduction to this lambda application, we obtain E for x in expression E prime. So operationally, this left binding and this lambda application appear to be equivalent. In the end, we obtain the same expression here. So one might claim that this left binding is just a syntactic sugar for this lambda application. But there's a big difference here. The difference is, in this case, we don't use lambda abstraction. There's no lambda abstraction involved. But here, we have this lambda abstraction where the variable x has polymorphic type. And if we go back to the syntax for left binding or predicative polymorphic lambda calculus, it's simply disallowed. This variable x must have a monotype. So first of all, this doesn't make sense even syntactically because it has polytype. So the first lesson that we learn from this comparison is this left binding is really new language construct that strictly expands the expressive power of the language. It is not syntactic sugar. So that's the first lesson. So we really extended the language predicative polymorphic lambda calculus. And the second lesson is this left binding is almost like lambda application. So we can think of this left binding as, in fact, this lambda application. Or alternatively, we may think of this left binding as this lambda abstraction that is allowed only in system F. So we temporarily allow a function that has this polymorphic type for its variable. So we temporarily create this lambda abstraction, but we require that this lambda abstraction should be applied immediately after its declaration to argument E. So it's okay to interpret this left binding as this lambda application where we allow variable of polymorphic type. But the restriction here is this lambda abstraction must be applied to its argument immediately. In other words, the declaration of the lambda abstraction must be followed right away, immediately, by the corresponding lambda application. So we place a restriction on the way that this lambda abstraction is used. So that's how we actually that's how we achieve partially the expressive power of system F, because now we can have this lambda abstraction with a polymorphic type, but we still want to maintain the decidability by requiring that this lambda abstraction be applied to its argument right away. So for instance, you cannot pass this lambda abstraction. So you cannot pass this lambda abstraction, which has a polymorphic type, where this variable x has a polymorphic type. You can declare this lambda abstraction in this language, but you can never pass this lambda abstraction as a first-class citizen. For instance, you cannot pass this lambda abstraction as an argument to another function. So you cannot pass this one to another function, or this function cannot generate a lambda abstraction like this one as a return value. So simply speaking, you are allowed to create a polymorphic lambda abstraction like this one, but you can never use it as a first-class object. You have to apply this polymorphic lambda abstraction immediately to an argument. That's the only permitted use of this polymorphic lambda abstraction. So we can think of this left binding as some restricted use of polymorphic lambda abstraction applied to an argument.